In this video, we will be talking about further details on our lecture 2. So, in lecture 2, we essentially derived an equation for our vectors which consists of the contravariant and covariant components of that vector. Now, we talked about this contravariant A1 and this contravariant A2 components, which are essentially the coordinates along this direction E1 and the other direction E2. But we haven't clearly talked about these A1s and A2s in this bottom part right here. We didn't talk about the covariant components of A1s and A2s. So in the previous video we have made a mistake. It shouldn't be we, it should be I have made a mistake that I wrote A1 is equals to del vector A by del x, but this is not the case. This vector A should be a function g, right? So this A1 is basically of the derivative of a function g. So what we are saying is that this A vector is the gradient at a point P of the function g. Now this del g by del x, A1 should be del g by del x evaluated at a point P, right? Now what is A2? This should be x1, I should say, because this coordinate is just x1 and this coordinate is just x2, right? We can write down the coordinates as x1, x2, x3, x4. I've established that in lecture 2, right? So A2 should be del g by del x. Now this is the covariant component, so del g by del x2 evaluated at a point, say P, an arbitrary point P, right? So this was the crucial details that was lacking in our lecture 2. So that is all done. Now let's talk about the metric tensor, right? In general relativity, you'll see something like this in the Einstein field equation, g mu nu. So what is g mu nu? Before taking a look at that, let's take the dot product of two equal vectors, right? Say v dotted with v, right? Now what is v dotted with v? Well, this is the modulus of v squared, right? We get the length of the vector v, and this is essentially the square of the length, right? So if we take the dot product, we can write our vector v in terms of its covariant and contravariant components, right? So see this part right here. Now v is just a normal vector, so it's just any normal vector, say displacement or velocity. These are sort of vectors, so these are normal vectors. So we can write them in this notation right here, this one right here. So this can be written more simply, like we'll contract this equation further. We can write it as ai e I, right? And this e is just a vector. So what happens when we write it like that, ai e I? Well, when we have top index and bottom index, we know there is this summation over I, right? So we get back to our original equation. Now, oops, I erased the a. Now let's write v in that manner. So we can write it as vi ei, right, dotted with, say, another index vj, because I don't want to mess up the indexes, or I should say indices. Now it should be ej vj. Now we could have written vi ei, but that would have mixed up the indices, right? So this is essentially summation once here and then summation once here. This is over I and this is over j, right? But let's remove that. Right. So let's just do the dot product of them. Well, this is basically the components vi, vj, and then we have the dot product of ei dot ej. Right. Now this vi, vj is there, and then this ei dot ej, this is what we call g of ij. This is the metric tensor for the respective coordinate system we have chosen. This is the metric tensor. Now let's talk a bit more on this equation. So we can write that modulus of v, we can write modulus of v squared is nothing but vi vj, and then we have g of ij in the front. Tensor equations, orientation doesn't matter in tensor equation. You can write g of ij at the back or you can write it at the front, right? So this magnitude of the vector squared could also be written as, say, we can write it as, say, somewhat ds squared, right? This is some sort of magnitude. ds squared is equals to g of ij, and then v of I, v of j, this can also be the length in the respective coordinates, right? So we can write dxi dxj. So this is our new equation. Why we have written v of I as dxi? Well, this v of I essentially represents a length. So we can write it as dxi because vi is in a particular coordinate, along a particular coordinate, and vj is along another coordinate, so we can write it as dxj. Now let's talk more on this metric tensor. Let's establish another equation. Say we have some sort of this vj, let's say a component v, I should call it, say, maybe v sigma, right? Now we are taking these were contravariant components, now we are taking the covariant components, right? Now let's multiply by, say, g mu sigma. Oh, one thing to note is that when you are dealing with Cartesian coordinates, this gij basically becomes Kronecker delta ij. Why? Because in Cartesian coordinates we have ds square is equals to dx square plus dy square plus dz square, right? We can write this as dx1 squared plus dx2 squared plus dx3 squared. So this is just writing it as we can write it as dx I dxj, right? We can write it as dxi dxj. Notice we don't have any component on the front, but when we will use another coordinate system we will have g of ij It's because the components on the front is just Kronecker delta of ij. What is the Kronecker delta of ij? Well, Kronecker delta of ij is nothing but a piecewise defined function where if it's 1, then it means I equals to j, and if it's 0, it means I is not equals to j. Right? So it means forcing us to set I equals j, meaning this would become dx. Since I and j are on the bottom index and I and j are in the top index, we can write it as summation over I and j, which would definitely become dx1 squared plus dx2 squared plus dot 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 as many coordinates we have in our coordinate system. So that's basically it about Kronecker delta function and the Cartesian coordinates, why we have Kronecker delta in the Cartesian coordinates. Right, so now let's prove another equation. Say we were considering v sigma, a covariant component of a vector v. Now let's multiply it by g, say mu sigma, and then we have g, say mu nu. Right. Now what happens when we multiply this? Well, we can, throughout tensor calculus, we will lower and upper our indices using this metric tensor, right? So if we have, say, g mu nu of v nu, this would cancel out this news and we would end up with v mu's, right? So throughout tensor calculus, you will find this operation going on over and over, right? So here this would be g mu nu, the sigmas and sigmas cross out, so we are getting g mu, sorry, not g mu, this should be v mu, should be v mu. Now when we have this v mu, so this should essentially, when we multiply by the g mu nu, this should be v lower index mu. But we can write this another way. We can write it as v nu, but set a Kronecker delta function of, say, sigma, no, sorry, say, we can write it as delta sigma nu of v nu, sorry, v mu, delta sigma mu of v mu. We can write it like that. Why? Because when we have Kronecker delta, if mu is not equals to sigma, then those components are 0. But if mu equals sigma, sorry, I've done some mistake right here. This isn't like that. Let's see where I've made the mistake. G mu nu, G mu sigma, V sigma. This should be V mu, right? And so we can write it as, oh, I see, I made a mistake here, sorry. So this should be mu's and mu's cancel out. This should be v new, which is equals to, say, we're writing it as v sigma and Kronecker delta of sigma new. So we're forcing sigma to be equals new, so this is basically v new, because all the other components, say, this equation is summed over sigma, right? So this should be 1 new v1 plus sigma 2 new v2 plus dot dot dot. So whenever new is equals to sigma, only those remain. Say new is equals to, new is some arbitrary number, say new is equals to 2, right? So only the 2, this part right here is gonna stay, and others, they are gonna be 0, right? So and what is the Kronecker delta? What is this part right here? This would be 2 of v2. So what is Kronecker delta of 2? Well, that's just basically 1. We have defined it. So when I is equals to j, that is equals to 1. So when new is equals to sigma, that becomes 1. So we are left with only v2, right? So that's basically it. So when we are writing the Kronecker delta function here of sigma upper index and new lower index, we are basically writing it like that to give v new, right? That's the same thing. Now if this equation holds, then we can say this equals to that, right? So this should be, let's write it in bottom, this should be g mu new of g mu sigma v sigma is equals to, say, Kronecker delta new v sigma. That's just equal because we have taken parts from here, right? So we can cancel out our v sigmas from both sides, so we're left with g mu new. G mu sigma is just the Kronecker delta with upper index sigma and lower index new. That's our new equation. Now what does this equation tell us? Well, it tells us that g mu new is just the inverse of g upper index mu sigma, right? That's why we have Kronecker delta of new sigma, right? So why is that? Like, why is it the inverse? How can we tell that this is the inverse of that? Well, because the Kronecker delta is just when sigma is equals to new, sorry, this will be sigma. When sigma is equals to new, that becomes 1, and when sigma is not equals to new, that becomes 0. Well, we know that say a matrix M times its M inverse is just the identity matrix. What is the identity matrix? Well, it's just 1, 1, 1s and 1s diagonally, and other components are just 0. So when sigma is equals to new, that means we are having this this diagonal full of 1s, and when they are not equal, those are zeros, right? So we have the identity matrix here, because when sigma is equals to new, we have the identity matrix. Sorry, we have 1 when sigma is equals to new, meaning this Kronecker delta is just the components, it's just representing the components of the identity matrix, right? And so that's basically it. We know whenever we multiply a matrix by its inverse, we have the identity matrix. So this g mu sigma must be the inverse of g mu new, right? Now let's talk a bit further about it. Say we have g mu new and g mu new. What is that? Well, from this equation we can see that our sigmas have become new, right? So this is basically the Kronecker delta of sigma sigma, or you can say the Kronecker delta of nu, right? So that's basically 1, because we can see that from these identity matrix components that turns out to be 1, right? So that's basically it about the metric tensor. In the next video we will be talking about the Christoffel symbols, and in the future videos we'll talk about how the Christoffel symbols appear in the geodesic equation. Alright, so see you on the next video.